Okay, get ready. Hey everyone, and welcome back. Ready to dive into something totally out there? We're talking about the search for axions.
Axions, yeah. They're these hypothetical particles, and physicists think they could be the answer to some big mysteries.
Mysteries? Okay, like what? You've got my attention.
Well, think dark matter. We can see its effects, like it messes with how galaxies rotate, but get this, we've never actually seen it directly.
So are you saying these axions, these tiny particles, could be like the missing pieces?
That's the idea, if we find them. And that's where the International Axion Observatory, or hold on, it's IAXO, comes in.
IAXO. Okay, say that again. How do you pronounce that?
IAXO. And specifically, we're looking at the baby IAXO experiment, which is being built right now.
A baby IAXO. Okay, that's a pretty cute name for something that's probably super complex, right?
Oh, it's definitely complex, but pretty cool too. Baby IAXO is designed to detect these axions, if we can catch them.
So how do you even start looking for something that's basically invisible?
Well, the key is they might not be totally invisible. See, we think the sun, yeah, our sun, could be making these axions.
Hold up, the sun is making these things. How?
It's all about what's happening in the sun's core, right? Crazy high temperatures, unbelievable pressure. It's so intense that light particles, photons, can actually sometimes turn into axions.
Wait, really? Just like that?
Well, it's called the Primakov effect. It's this whole thing where a photon in a really strong magnetic field can basically transform into an axion.
Okay, so the sun's making these axions, and some of them are headed our way.
Exactly. And that's where baby IAXO comes in. It's waiting to hopefully catch them.
Right, so how does it do that? How do you catch a particle that's almost a ghost?
Okay, picture this. A giant magnet, I'm talking massive, like longer than a school bus, 10 meters long. That's baby IAXO's secret weapon.
Okay, a huge magnet, that's cool and all, but what's so special about it?
This magnet can create an insanely strong magnetic field, and get this, when these axions we're talking about, when they pass through it, there's a chance, a tiny chance, they transform back into something we can detect. X-rays.
Whoa, so it's not actually seeing the axion itself, it's looking for a clue, like a little X-ray blip to say, hey, I was here.
You got it. But, and this is a big but, those X-ray signals, they're super faint, like trying to hear someone whisper in a hurricane.
So how do you hear something that quiet? What's baby IAXO using? Some kind of super-powered microphone for X-rays.
Okay, so imagine, instead of my microphone, you've got these super sensitive detectors, and they're called, get this, micromegas detectors.
Micromegas detectors, that sounds intense. Kind of like a superhero gadget. So what makes these detectors so special?
These detectors are incredible. They're designed to pick up even the faintest X-ray signals, even with all the cosmic noise going on.
Cosmic noise, so what we're dealing with is like trying to hear a pin drop in the middle of Times Square. Right.
Exactly. And these micromegas detectors, they're like having, those noise-canceling headphones. But for X-rays, they filter out everything except that tiny signal we're looking for.
A signal that says an axion was here.
Right. Yeah. They're searching for an X-ray signal with a very specific energy signature, one that we'd expect if an axion transformed in the magnetic field.
It's like detective work, but on a cosmic level. So you said before that baby IAXO, this is like a test run for a bigger experiment, right? IAXO?
You got baby IAXO is kind of like the prototype, so we can test everything out before we build the big one, and IAXO will be bigger, way more powerful with a much bigger magnet.
Okay, bigger is usually better, but why? Why not stick with baby IAXO if it's already capable of finding these axions?
Well, remember how we were talking about those X-ray signals, how faint they are? Even with baby IAXO, the chances of catching one are still, well, they're not great.
So it's a matter of increasing the odds. The bigger the experiment, the better the chance of finding something.
Exactly. A bigger magnet in IAXO means more chances for those axions to convert to X-rays, and with more detectors, we can be much more sensitive to those signals.
So it's all about casting a wider net.
Right, exactly. Like trying to find a message in a bottle, but the ocean's the size of the universe.
Okay, so let's say everything works perfectly, baby IAXO, then IAXO, and we find these axions. What changes? What do we learn?
Oh man, that's the really exciting part, right? Just finding them, that would be huge, like potentially solve the mystery of dark matter, but it doesn't stop there.
No, there's more. What else can we learn from a tiny particle?
Okay, think about it. These axions, they were created like way back in the beginning, fractions of a second after the Big Bang.
Okay, now you're talking about cosmic time travel. How does that even work?
Well, Not exactly time travel, but close. See, these axions, they hold information, clues about what the universe was like way back then.
So by studying these axions, we're actually studying, what, the beginnings of the universe itself?
In a way, yeah. It's like they've been traveling through the universe since the beginning of time, carrying secrets about how it all started.
So it's like these tiny axions. They're like little time capsules just floating around out there, holding on to the universe's secrets.
Yeah, that's a great way to put it. And there's more. Remember that strong CP problem? Axions might be able to explain that too.
Okay, the strong CP problem. Remind me what that was again.
It's like this. There's this type of symmetry violation that should exist according to physics, but we don't see it, like, anywhere in the universe.
Right. Okay, I remember. It was a head scratcher. So how do axions fit into all of this?
Imagine, say, a spinning top, right? Our current theories say there should be these tiny wobbles, but we don't see them. Axions could be acting like, I don't know, like a stabilizer or something, smoothing everything out.
Wow, okay, so these little invisible particles might actually be the reason the universe looks the way it does. That's kind of amazing. But, okay, let's say we find these axions, we learn about the early universe, we solve these big physics problems. What's next? What's the practical side of all this?
That's the thing about fundamental research, right? Sometimes you don't know the practical application right away, but look at history. These big discoveries, they always lead to something incredible down the line.
Yeah, it's like the more we learn, the more we realize how much more there is to learn.
And who knows what amazing technology might come from discovering axions. Think about it, discovering the electron. That led to, what, everything. Computers, smartphones. Axions could be just as groundbreaking.
It's like opening up a door to a whole new world of possibilities. Well, I have to say, this deep dive into axions, baby IAXO and IAXO, it's been mind-blowing.
What I find really inspiring is how everyone's working together on this. Scientists, engineers all over the world trying to unlock these mysteries.
Absolutely. It really shows you what we can achieve when we put our minds together. Well, that about wraps it up for this deep dive. To our listeners, I hope this sparked your curiosity about axions and the amazing research going on at IAXO.
It's a good reminder that sometimes the biggest discoveries come from the smallest things.
Well said. Keep those questions coming, keep exploring, and we'll catch you next time on The Deep Dive.